let's continue our discussion of section 2.10. So what we want to do first is negate quantifiers. So we saw this a little bit in the examples in the first video we saw. So let's think about what happens when I negate a statement of the form for all x in S, p of x. So just in words, right, I'm going to say for all or for every x in the set S, p of x, and I like to write is true just to remind us that we have some statement which is going to be true. So now let's think about what happens if that's not true. So it's not going to be true that for all elements in that set, this statement is true. Right? So if it's not true for all of them, that means there's at least one of them it's not true for. So it doesn't have to be true for, it doesn't have to be false for every single one. There just has to be one that it's false for. So I would say there exists some element where that statement is false. So when I negate that for all, I end up with that there exists. So the for all becomes that there exists. And then I negate the p of x. So I get not p of x, or p of x is false. So let's try that with an example. This example says for every integer, 2x is greater than x. Right? For every integer, 2x is strictly greater than x. And we know that that's not going to be true. I'll give you a second to think about why that's not true. Right? For example, we just need to show one thing it's not true for. When x equals 0, 2x is not greater than x, because 0 is not greater than 0. So it's not true. This overall statement isn't true because there exists some integer from that same set such that 2x was not greater than x, or usually instead of writing not greater than, we wrote less than or equal to, because that's a negation of our not greater. So I'd say there exists some x in C such that 2x is less than or equal to x. So again, when I'm negating here, my for all becomes that there exists, and then I negate that statement. The opposite, the negation of that greater than, is a less than or equal to. Let's look now at the existential quantifier. So we have the statement, there exists some x in S such that p of x is true. So there exists some x in S such that p of x is true. All right, so let's start to think about what it means if that's not true, right? There does not exist some x in S. So let me just make it clear that I'm negating this here. I'm not writing the same statement. There does not exist some x in S such that p of x is true, right? But that's not a very good way to write it. Instead, I might want to write, there's none of them where this is true. Therefore, for all of them, it's false. So for all x in S, p of x is false. That's my nice negation in words. So if it's not true that there's one where this statement is true, then for all of them, this statement must be false. So I can say for all x in S, negation of p of x, not p of x, which is, right, not p of x really means that p of x is false. So let's try that. Here we have the statement that says there exists an integer. We always put a such that after the there exists, such that 5x minus 1 is equal to 0. Well, we can think of that, right? If I take an integer times 5 and then minus 1, I'm never going to get 0. Because if it was true, then I would have to get that 5x would equal 1, which means that x is equal to 1/2, right? That's the unique solution to this. but that's not an integer. So just sort of considering this statement, right? Which means its negation should be true because the original statement was false. It wasn't true that I had this integer such that this was true. So for all integers, let's write it in words first. For all of my integers, this isn't true. 5x minus 1 is not equal to 0. Or for all x in z, 5x minus 1 not equal to 0, if I want to write everything in symbols. So the big thing to remember here is when I negate a there exists, it becomes a for all, and then I just negate the statement that's next to it. So here's a discussion question for you to look at. So for each of the statements below, I want you to write the negation in words, and then I want you to write the original statement in symbols and the negation in symbols, and compare those symbols that you have to those words that you've written down. So we want to look at the statements. The square of every real number is non-negative, and just a quick fix there, every integer is either even or prime. The last thing that we're going to talk about in this section is negating a conditional. So perhaps you remember that we saw that the statement P implies Q is logically equivalent to the statement not P or Q. And I've got a truth table over to the side here, right? In order for P implies Q to be true, either P was false, or if P wasn't false, then Q had to be true. So we can see that not P or Q has exactly the same truth table as P implies Q, so therefore those are logically equivalent. And now if I want to negate P implies Q, I know that's just going to be the same as negating not P or Q. So when I negate that, we like to think about this as distributing that negation to each symbol, although that's not really what we're doing, but it is how it kind of looks. So I get not P. The negation of an or becomes an and then we get the negation of the Q. Now if you have the negation of the negation, it swaps that true to false twice, so it's back to where it started. So that's the same as P and not Q. So we get that P and not Q. All right, so why is that true? Could we have seen that another way, right? The negation of this P implies Q, it needs to be true exactly when P implies Q is false. So this is true when P implies Q is false, which is when, let's check, P implies Q is false exactly when P is true and Q is false. That's the only time, right? So P is true and we get not Q. So that's another way that we could see or that we could think about this negation. So whenever I'm thinking about when a implication is not true, in order for it to be not true, the hypothesis must be true. So we need, for it to be not true, the hypothesis is true and the conclusion is false. So that's the only way then if then can be false. So then my implication is false, which means the negation of the implication is true. Let's go ahead and practice with a symbolic negation here. So I want to negate this sentence. So I'm going to do the negation of, for all epsilon greater than 0, there exists a delta greater than 0, such that x minus a less than delta implies the absolute value of f of x minus f of a is less than epsilon. So I'm trying to negate that whole sentence. So we're going to go step by step here. So first I'm going to negate the for all. Whenever we negate a for all, we just change it to a there exists. And the thing that comes after it stays the same. And now I need to negate everything that comes after that. Right, so I'm just sort of showing my steps here as we go. So I'm just rewriting everything else, and I still need to negate this in the next step. So you're welcome to kind of go through and do this as you go. Let me write the same thing as I had before. All right. So put it in that bracket. Okay, now we'll go ahead and bring that next negation into the there exists. So I get there exists and epsilon greater than 0, such that the negation of that becomes a for all delta, still greater than 0. And now I need to negate my if then. X minus a less than delta implies magnitude f of x minus f of a less than epsilon. In order to negate that if then, I have to have p being true and q being false. So I get for every epsilon greater than 0, there exists delta greater than 0, such that x minus a is less than delta, so I keep that the same, and the q is false. So not f of x minus f of a is less than epsilon. So what does it mean that this is not less than epsilon? It means that x minus a is less than delta, and this quantity, if it's not less than epsilon, then it must be greater than or equal to epsilon. So finally, this is the negation of that statement. Again, if I tried to just do it all from the beginning, I distribute kind of that negation to the for all. That becomes a there exists. I go to the there exists. That becomes a for all. And then if I think of this as P implies Q, maybe I'll do it all in the same color here. The negation of a P implies Q is P and not Q. So I left that P the way it was. I put in my and then I had that not Q. Here. So that would be that negation. So this is a definition of a thing that you might have seen before. So we'll talk about this in class, but if anyone wants to prepare, they can earn a challenge point by saying what this is the definition of. It's similar to one we had in last class, but a little bit different. All right, for your final discussion question here, we've got a beautiful table for you to fill out. So I've put in some entries here. This one has some statement in symbols. This one is a statement in words. And here is the negation of some statement in words. And I want you to just fill out the other entries in each of those rows. So for each statement, you'll have to take it from words to symbols, the negation in symbols, and the negation in words. So I want all four of those for these three statements.